All right. Good morning, everybody. Today we're going to talk about calcium-based ceramics. And my paper was on the 3D printing of porous hydroxyapatite scaffolds intended for use in bone tissue engineering applications. It was done in the United Kingdom at I can't remember the university, but the scope was to examine the feasibility of using 3D printing to on hydroxyapatite using polyvinyl alcohol as a binder, as opposed to the traditional binders that are usually used. And they wanted to know if the 3D printing process could produce stable scaffolds and what the mechanical properties of these scaffolds were, and how the scaffolds promoted cell growth, and whether different sintering methods would affect this. So the material is hydroxyapatite. You can see the chemical composition up there. They chose this material because it was most closely related to the material of bone, and they thought it would be the most beneficial for cell growth. And the binder they used was polyvinyl alcohol, and it was processed. I think it was ball shoot ball milled. Yeah, sorry, lost that for a minute. It was ball milled so that only particles of less than 200 micrometers were present, and they chose this binder because, unlike the beta triphosphates, it was less toxic, because those have been shown to produce minute levels of toxins after they've been post-processed. And the process conditions they examined the powder and the powder different combinations of the hydroxyapatite and the PVOH, and how the different viscosities worked and how they flowed, and also the mechanical strength of the samples, the scaffolds. And these are the scaffolds they made. They're 10 millimeter diameter by 10 millimeter diameter by 10 millimeter in height, with 1 millimeter rectangular pores. And this is the external structure, and this is the internal structure. And they use standard scanning electron microscopes, CT scanning, and spectroscopy to analyze the parts. They used a Z printer 310, which I'll go back to the first picture, and it's basically a binder jetting on a powder bed. The printer lays out powder on the bed, and as it comes back across, it prints the binder jet on the path, and then once it gets past, the base lowers down and the process starts over. So the first thing they wanted to look at was the scaffold characterization of the parts they produced. They attempted to use different weight percentages of hydroxyapatite, and the only two that were able to produce samples at all were the 50% hydroxyapatite and the 60%. And they found that the 60% samples were so dry and brittle that they couldn't get the extra powder out of them. It resulted in too much degradation, so the only ones they were able to test were the 50% samples. And as you can see from the graph over there, the sintering, the 50P, the 50F, and the 50V correspond to P was just the printed, F was sintered in a furnace, and V was heated in a vacuum heater, and the 2 and the 6 correspond to the 2 hours or 6 hours of heating. And the X and the Y were the print direction along the axis, which axis they chose for the print direction. And the X-axis parts for all samples showed decreased shrinkage, more uniform shrinkage between diameter and height. The Y-axis printed samples showed more shrinkage in the height than they did in the diameter. But they all were fairly similar in weight loss percentage, within 2%, which the study considered small enough to be viable. And then through the electron microscope, they were able to scan the the micro images and see that there was no chemical change in the hydroxyapatite after sintering, which ensured that it was, I guess the way they kind of put it was that there was no cross-linking between the layers, which would have changed the microporosity, and they said that was a positive result. There were surface pores for the x-axis parts were a little bit smaller than the y-axis parts, and they said that was because of the drying process and the way the layers were oriented. The drying process affected the surface pores, which corresponded to what I'll talk about next, which was the mechanical properties. So they did a compressive test on 3 samples of each type, and they found that the x-axis parts and the y-axis parts failed in different ways. The x-axis parts had crack propagation along the layers, which resulted in a catastrophic instantaneous failure basically, where it just kind of collapsed. And the y-axis parts showed plastic failure, plastic deformation as the load increased. But they did see that the y-axis printed parts showed superior mechanical properties, higher ultimate and yield strength. The next thing they looked at was how does the post-processing affect the porosity of the parts, whether the vacuum oven or the furnace. And what they found was while the x-axis scaffolds produced a smaller surface micropores, they were all deemed suitable for further study because they all showed unintentional, or I forget how they phrased it, but basically unintended micropores that weren't the 1 millimeter squares that they had designed. And the way they studied it was they took a grayscale image and they kind of determined the level of grayness in the picture, and that was how they determined how much porosity was in each region of the sample. And they said, while this isn't normally a porosity technique, it was good enough for what they were doing. And you can see the number of pores is relatively consistent for, this is for one sample, across the different areas of the sample. And the x-axis parts showed a greater volume fraction of I want to say of HA than the y-axis samples. So in conclusion, they just said that the 3D printing process was viable to produce bone scaffolds. Post-processing significantly improved the mechanical properties, making it stronger than just a pile of powder. And internal porosity of scaffolds is promising for bone growth because of the surface roughness. The paper was very detailed. I had to look up a lot of words, but the graphs were kind of, you had to like flip back 4 pages to find the graph they referenced instead of kind of putting them there where I thought they should have been. But it showed promising results for future studies. This study was kind of just, can we build it, and does it even make sense to move forward? And it was interesting to see that it was positive to move forward. But one thing I noticed they mentioned was the powder they used. They mentioned at one point that it was a calcium deficient hydroxyapatite powder, and they also didn't do any processing on that powder, although they did do processing on the polyvinyl alcohol. So I was curious to see if a processing of the hydroxyapatite powder would have affected anything, made it stronger or more uniform bonding. So that would be another study I would like to see done.